But actually Cantor got it another way. He said from Mengen, see, I'm freely interpreting that Cantor was really a precursor to category theory. As he said, well, there are these Mengen, pretty complicated. But notice in particular, I've got this brilliant idea. We can extract from a Mengen, we can extract just some bare dots. He calls them lauter Einsen of Deutsch. Lauter Einsen. We can extract that. Then we'll have this amazing property that the points in the plane and the line become the same because the abstract thing that we extract from them, I can show are isomorphic. Using an idea I learned from Steiner, by the way. He says I learned from Steiner. Anyway. So, and then he calls the result cardinale, by the way, which is not yet the equivalence classes. He knows about the equivalence isomorphism classes, yes, but the cardinale, as I understand it, not. They're what you get by. So this is but this is kind of a double negation. And I'm saying that Cantor negated this vague idea of Mengen by saying, let's look at things that have no cohesion. I mean, the Mengen are things that have cohesion and variation. We study in mathematics all kinds of things that have cohesion and variation. You negate that, you come to the abstract sets. The double negation is, you can actually use the abstract sets as a basis for modeling all kinds of things. By looking at the idea of structures in abstract sets, you can have not only algebra, but even topology, even models of cohesion itself. Something that's modeled in that. So let's see what that means. So we start with E, the Mengen. It's a version. So I'm saying it. The double negation involves the idea that Mengen come in many categories. As I said at the beginning, you need, with Maxwell, to screw up or down the precision, or use the maximum technology we need, or the minimum technology we need. And that's a variable. So there's not just one category of Mengen. No, all of the cohesive topos should be thought of as different levels. So, but anyway, we start with one. We start with the cohesive topos. E is a topos satisfying my axioms, for example. Although from what I'm saying, it could be much more general. Now, we want to find within that, some spaces that are devoid of cohesion and variation. Imagine that the original objects had some specific category. And again, the word category is some kind of cohesion and variation. But among those, there ought to be the ones that are relatively trivial. Qualitatively trivial. Oh, I forgot to say one thing. I forgot to say one thing about my third axiom. Everything can be embedded in a connected thing. That implies that the cohesive topos is very much not the U that underlies it. Because here, the truth value object is getting killed off. This is not an isomorphism. It's very qualitatively different from an isomorphism. Or the whole thing collapses. Everything is totally trivial. But if it's not trivial at all, then it's very different. Very, very different. So it's not just some arbitrary subcategory we're looking for. It's something like that. So, and then, yeah. Let's start over. Yeah, the idea that mathematical objects are structures, as I already said, no, they're objects in the category. But they can be represented as structures. Represented usually means something of the following sort. But in order to do that, we have to find two parts of E. The discrete part and the connected part. But defined by this orthogonality relation. Given any two objects in the Cartesian closed category, we can look at the function space s to the power d, and there's a canonical map from s to that. If you like, it's induced by the map from d to 1 in the exponent. It's like these are the names of maps, and among those there are always the names of the constant maps. So this equation is saying all maps are constant. All maps from d to s are constant. So this simple idea, from which it's easy to see, for example, that if you take such an s to any power x, then it still satisfies the relation with respect to the same d's, because this is s to the d to the x, but s to the d is s to the x. It's just like algebra. It's just fun. Exponential rules. Given a d, the s's are closed under raising to any power, any x. Similarly, for example, the s's must be closed under products, because if the s's, two s's are orthogonal to the same d, then since this is s1 to the d times s2 to the d, and that's s1 times s2. And so on. So there are certain closure properties automatically if you have two classes that are orthogonal in this sense. And if you have two. For everything in this class and everything in that class, you have this relation. Now, typically this is known as a Galois connection. The Galois connection can be generated by a few objects on either side. So for example, if you suppose, as we were doing before, that U is given, you can define D to consist of all the D's to satisfy this with respect to all the S's of U. And those you might want to call, let's say, D connected. Are U connected? The idea is, of course, that somehow, if you want to parameterize motion by D, then the only motions that are in S are trivial. You can't get anywhere because D is so discrete. Or because D is so connected. Those are sort of dual reasons. I guess this is a familiar idea. But on the other hand, if you start with some objects in D, just some objects, then you can define the U to consist of all things, all the S's that satisfy this, D, and then define script D to consist of all the D's that satisfy this with respect to all the S's. A well-known game with Galois connections arising from an arbitrary binary relation. Take this as your binary relation. Now, the thing is that for algebraic geometry, analytic geometry, smooth geometry, and many other examples, this whole thing is generated by one object, P, namely the infinitesimal space with 1 point and 1 degree of infinitesimal variation. So it's like Heraclitus is trying to move in one direction. There's just one object, D, which is like, well, it comes from Heraclitus, from Hegel, from everybody. In other words, it's the idea that in the real world, there's something called motion going on. Motion means to be in one place at one time, but not only in that place. If we abstract from all the motions that we ever heard of, we have this idea of the D. So we import from reality, rather than constructing by starting with an empty step and applying mental things, we have this concept. There's still a total distillation of the idea of motion. We import that from reality and say it must be in our local scheme. It's an object. Then, of course, the problem is to find out all the properties that you have, starting from this point of view, but in particular, we can use that one object D to define define a notion of discrete. And if you like, you could think, you could call it, say, infinitesimal discrete. Or we think of D as infinitesimal. It turns out, by the way, that this, okay, such a U defined that way. Again, going back to the general class E, no matter what. You'll always have the pi lower sheet preserving products. Because, I think I mentioned this before, it's a general property of all inclusions. But if the subcategory is closed under exponentiation by arbitrary objects, then the left adjoint preserves products. So I don't just get a category U closed under those properties. In particular, I get a component of pieces functions that preserves finite products, which I need for all sorts. So that action is proved automatically. And even that doesn't depend on D being small in this sense. It's a single object. Now, there is this whole story, I don't have time, about D being an atom. There's a further property, so it's silver interpreted adjoint and so forth, which happens to be true in those three great infinitesimal theories, differential, algebraic, and analytic, which implies more property. It implies that they're further adjoints. So, I think of, in some sense, the P lower sheet, the left adjoint, which does sort of automatically exist in the sense that after all the S's are closed under arbitrary limits, really. The same calculation goes just as well for arbitrary, because this is the right adjoint. So modulo some usual assumptions. The inclusion has a left adjoint, called P lower sheet, called components. And this is by construction, because the U is defined in this way, that reflection automatically preserves finite products. In some sense, the first thing you come to is the inclusion of these S's and the left adjoint. Which I sometimes, I think of as counting trees. It's another way to think of these things. If your object X is a forest, you want to analyze the wood in it, you might take as a first step just to count the trees. In general counting, I want to count people here. I don't count, human flesh. I count the components of human flesh. That's too personal. But I mean, right? You count, when you talk about counting things, you're treating the things as points. Same sort of thing Cantor wanted to do with the left adjoint. So you're treating the things as points, even though what they actually are is probably components with respect to something. If you count them with respect to nuclear physics technology, you'll get more pieces than if you count them according to classical chemistry technology. It depends on the topos you're in.
Listen here for a second. Just to give you, we have more or less 10 minutes more. It's kind of that, okay? We have to leave the building at a certain point, so on.
Oh, yeah.
So, can you, maybe a bit more, but...
Well, anyway, look, and this is just an indication of how you can analyze this thing further. You can analyze E, then, as consisting of functors from D into U by the way of looking at the Hom objects. Arbitrary objects in E have Hom objects, which are then pushed down into U by the points functor. That's the usual way of view. So if you choose a subcategory of U sub 0, which can be quite small, which is sufficiently large, then by the standard method, you get a full representation of E. So to be a space then becomes a property. This is a kind of structure, the limited as a kind of property, so now you reconstruct it. So I'm back to the model reconstructed as a property of the structure. The structure is determined by the D0, by the figures of certain simple connected shapes.